This is the first in a series of videos about solubility. We are going to talk about the solubility and the forces that affect it, which are the intermolecular force strength, the pressure, and the temperature. So solubility we represent with the letter C because S was already taken, standing for entropy. So we're using C for concentration. Let's define that. So solubility is the max concentration of a solute in a solvent and that has to be at equilibrium. So it's the most possible amount of solute that we can squeeze into that solvent, the highest amount. So if we were to make a number line and we were to put C right here, so C is going to be our solubility. We can look at we can give different names to the situation where the concentration is in relationship to the solubility. So let's say we're over here and the concentration is less than the solubility in our flask. So it would probably look something like this. We'd have our flask. We'd have a few molecules of solute, probably not that many, but a few. And lots of solvent. So we would call this unsaturated. And there are even degrees of unsaturation. So if we were very, very, very unsaturated, like this picture that I drew, we call it dilute. And if we were only a little bit unsaturated, we would call it concentrated. Okay. So if our concentration is below solubility, we are unsaturated. If our concentration is at the solubility, if we make it right at that point, that is called saturated. The concentration is equal to solubility. And what this picture is going to look like is that we are going to have the maximum number of particles here in our solution. And there's going to be a bunch of solvent. But just to make sure we have the absolute maximum number of particles, there's going to be a little red hump at the bottom. There's going to be a little bit of solid sitting at the bottom that is constantly redissolving and depositing back as a solid. So this is to make sure that we have the maximum possible in the solution. Okay, and then, surprisingly, there is a third description, and that phase is called supersaturated. And I know what you're thinking. We have already reached the maximum number. How can we possibly go over the maximum number? How can the concentration be greater than the solubility? Well, the reason is because this is a non-equilibrium state. So we defined solubility and said this is the maximum concentration at equilibrium. So we can pack in just a little bit more at a non-equilibrium state, but the maximum at equilibrium is still C. It's still that much. So let's say it was non-equilibrium, we were able to pack in a few extra particles, more than would usually be able to fit, like putting 4 people in the back seat. It's a little bit sketchy. It's a little bit unstable. So that's why we put this asterisk, this star up here. It's kind of an unstable situation, and it only takes a small amount of force to push this back into the saturated state. So one of the forces, this could be something called a nucleation site. So we can add a nucleation site by scratching on the side of the glass with a stir rod, or scratching on the bottom, or if you added a crystal What we're trying to do is add extra surface area where these particles can nucleate and crash out. And then we get precipitation, and we return to the equilibrium, fully saturated phase. So more on this in equilibrium section, but this is something that's relevant to my nanochemistry research. Okay, so we have talked about saturation and how saturation is when concentration equals the solubility. So what do we know about solubility? We know what it looks like now because of the pictures, but what kind of environmental factors affect how much can be dissolved? Can we dissolve 1 gram in 1 liter solution? Can we dissolve 10 grams, 100 grams? What affects that? So it varies with the system, and it varies with the strength of the intermolecular forces, both of the solute and of the solvent, like we talked about in the last video. And then within a particular setup, you can vary the pressure and the temperature. And this is something we do in the lab all the time when we're trying to change how much of something we can dissolve in something else. Okay, so the first of those factors is the intermolecular force strength. Now, you've probably heard about this in high school and you just don't know about it. You might have heard a phrase called like dissolves like. That's what this is about. We're about to make it slightly more scientific. So the phrase goes, like dissolves like. And in this chapter, the science version of that would be solvents, the larger piece, dissolve similar solutes, the smaller piece. So a lot of S's there. Solvents dissolve similar solutes. So if the intermolecular forces are similar, then it's easier to dissolve something in something else. So when we talked about intermolecular forces, we talked about dispersion forces, polarity, and hydrogen bonding, which is a special kind of polarity. And so if the polarity is similar in the solvent and the solute, you are going to get something that's dissolving. So an example of a polar solvent and a polar solute, we could have water as our solvent, dissolving ethanol as our solute. This is any kind of beer, wine, vodka, alcohol that you would drink at the store, that you would drink at a bar, I mean. So here's our molecule, H2O, and here's ethanol. Also got an OH group, and then it's got 2 carbons with some hydrogens on the side. There we go. Okay, so if we look at the type of forces, we know that the dipole for water is going to point in this direction, and the dipole for ethanol is going to point towards this oxygen over here on the left. So there's a pretty sizable dipole for both of these. So both of these are going to be polar. We're going to see dipole forces present. And if you notice that there's OH groups are extra strength dipole forces, hydrogen bonding. So there's hydrogen bonding acceptors here and donors on the water. And on the ethanol, there's a hydrogen bond donor and acceptor as well. So it also has hydrogen bonding. So they're super duper similar. They're very much alike. So ethanol is going to dissolve easily in that water. All right. So let's look at the other kind. Let's look at nonpolar molecule examples. So nonpolar dissolves nonpolar. And you probably haven't used too many examples of this yet in your young science career, but as you move into organic chemistry, nonpolar solvents will become your friend. So here's an example of a solute, CCl4. And this can dissolve carbon dioxide. And to prove that they're nonpolar, let's check out the structures here. Carbon is going to be tetrahedrally coordinated to 4 chlorines. And in CO2, carbon is in the center of 2 double bonds to oxygen. Okay, so if we look at these, look for dipoles here, we can see that there's a little dipole for each of these bonds pointing towards the chlorine. But because this is tetrahedral, there's no net dipole. All of those dipoles cancel each other out. And the same is true for this one. We can draw a small dipole for each of the bonds pointing towards the oxygen, but they're equal and opposite in direction, so there's no net dipole there either. So the only intermolecular force left with no dipole and no hydrogen bonding is dispersion. Dispersion is the only intermolecular force that's worth noting in this case. And because both of these two molecules have only dispersion forces, CO2 will dissolve in CCl4, like dissolves like. And our last example is of unlike, doesn't dissolve unlike, which doesn't really sound very good, and I can see why no one ever says that. So if we mix polar and nonpolar together, nothing's going to happen. They are not going to mix. One is not going to dissolve in the other. And the example here is salad dressing. We'll draw a slightly fancier container because, of course, this is salad dressing and not just like water in the laboratory. So a common salad dressing is an oil and vinegar dressing. And you notice that when it's sitting in the container, it often separates into 2 layers, kind of yucky looking, but still tastes good. We persevere. So our bottom layer, that's going to be the brown one in the salad dressing. That one is the vinegar layer. And vinegar is acetic acid dissolved in water, and water is polar. The top layer, that's going to be your oil layer. That's the yellowy one, and oil is nonpolar. So what we see when we mix together 2 things that don't have very similar intermolecular forces is that we get separation. They refuse to mix. And when these are 2 liquids, this is called immiscible, which is like the fancy way of saying unmixable. So they don't mix together. One of them does not dissolve in the other. The intermolecular forces are important to predicting whether one substance will dissolve in another substance. And in the next video, we'll talk about pressure and temperature, which will affect how much of something will dissolve in something else.